from the break. I hope you recover yourself and have some good rest. So this is the first lecture from this 5-lecture course, which is quantum gases and superfluidity. So I said already this morning what would be in this course, so I will not need to repeat it now again. Let me start directly with specifying our sandbox where we will play with and make more clear what would I mean by saying these quantum gases. Yeah? First of all, we have a gas, and normally I will not consider atoms, so it will about cold atoms. I will not consider atoms in a trap. So I will just make at some point few comments on that. So what I will do, I will consider similar to what was in the lecture of Jean-Michel. I will consider n atoms, of course identical atoms, fermions or bosons. For fermions would be, we will need 2 species. For bosons would be sufficient 1. So n atoms or particles in a box V, which is L cross L cross L. And of course, in the end, all formulas becomes particularly simple in this so-called thermodynamic limit, where both N and V goes to infinity. But I fix, of course, the concentration N, which is their ratio. This is fixed. Yeah. So what does it mean, quantum gases? So when we consider, let's formulate these things and all the conditions we will work with in terms of length scales. So when we have a gas of with a concentration n, we have a typical length scale which is n, so length scales. Relevant length scales. First of all, we have n minus 1/3, we're in 3 dimensions. Yeah? In 2 dimensions minus 1/2. In 1 dimension on a line n inverse. This is a mean interparticle separation, I guess. Yeah? So this is mean separation. Then, of course, we are typically thinking in terms of gas at some given temperature. Yeah? Thermal equilibrium at some given temperature. So we will have temperature T. In all the lectures, case Boltzmann equals 1. So I measure energy and temperature in the same units. But this, of course, we know. For this, we can identify the following lengths, which is a thermal de Broglie wavelength, which is h bar. I don't bother myself with the coefficients 1, 2, pi, etc. So which is h bar over thermal, typical thermal momenta, which is, of course, square root of m temperature. So forget about 2. Yeah? And of course, on the other, the third length which we have, of course, when we consider interacting gases, so we have some interparticle interaction. We will consider in my lecture only these atoms, so that means short-range interaction, which decays like 1/6, and not consider dipole interaction, dipole forces, which are a bit special in this case. So this V of R1 minus R2, this is interparticle interaction, short range, and then, of course, here we have a typical range, R0. So this is interaction range. As you will be explained next week in the lecture of Jörg Valraven, so all about scattering. So typically we will, R0 would be in most of the cases, except you are not close to the Feshbach resonance, more or less the same as the scattering length. Yeah? This is scattering length. S wave. So actually these 3 quantities, these are a relevant length scale in our case. So let me now set the relation between them for this course. First of all, we want quantum gases. That means that our de Broglie wavelength should be at least comparable or larger than the mean interparticle separation. Yeah? only then particles recognize themselves as bosons or fermions, and you have these bosonic or fermionic statistics. Otherwise, you are in the regime of the Boltzmann gas, yeah, which is not that interesting for our purpose. So now if I plug in the quantity lambda t in this form, then of course from here you immediately find that there is a typical temperature T star when this becomes comparable. Yeah, and from here you will immediately see that this is h bar squared over m density to the power 2/3. Yeah, which is actually some sort of Schrödinger relation. This distance gives you uncertainty in momentum, h bar over this one, and h bar squared, p squared over, yeah, that's exactly this one. So this is temperature below which, so this is when this lambda t becomes of the order, yeah, below which quantum, above classical. And that's exactly, you know what it is for bosonic gas. This is roughly estimate for the temperature, critical temperature of the BC. Yeah, for fermions, fermionic gas, it's a Fermi temperature. Yeah, where the particle starts forming a Fermi C, and so their distribution in momentum space starts deviating from Gaussian 1. It becomes closer to the Fermi step function, Fermi surface. Okay, so we are in this regime when we want to be quantum in the first place. And second, of course, when we want to have a gas, that actually means that you want to have that n minus 1/3 average interparticle separation has to be much larger than the size.
What was the difference between T star and TC?
Numerical coefficient.
Okay.
And the physics. Yeah, for bosons it's Tc, for fermions it's T Fermi. But it's a T star is a temperature below which you see quantum effects with all the consequences. Huh? So then this is the gas. And actually, if you compare these two things, yeah, that n star in inverse is much smaller than lambda t, that you will see that here you are actually comparing the lambda t versus n minus 1/3. You will immediately recognize the typical momenta that you have. Yeah, so you have here low energy collisions. So that means typical momenta times R0 over h bar is much smaller than 1. And for those who knows, for those who doesn't at the moment, they will know at the end of the next lecture, next week, but after the lectures of Jokval-Raven, this means low energy collisions that is synonym to the S-wave collisions. So that means only actually S-wave channel dominates, all the others are suppressed by these small factor squared. All the others are subtracted by the power to L, all the other channels. So S-wave dominates. We have S-wave collision, and this actually will help us very much. In most of the cases, we can replace all the complicated potentials, interatomic potential, by contact one. So which mimics for you in the Born approximation S-wave collisions, where G, in most of the cases, is just 4 pi h bar squared over m times A. There would be two cases where I have to be very careful with that. So, so I will show you where it breaks down. So typically, this substitution only works, it's a kind of a contact potential. It works when you should not go beyond the first order. It is designed in such a way that the Born approximation gives you the exact answer for the scattering. Normally, you have to solve the Schrödinger equation or to sum up this Born series for scattering. So instead of this, you just take the Born approximation and this then the answer. Yeah? But you don't go with this to higher order. If you have to higher order, in 2 points we will have to go to higher order, things becomes a bit more complicated. But not that we cannot solve it. Okay, so this is now a starting point. We have gas, or in other words, I can put here A, doesn't matter, and we have low temperatures. This is, so therefore we also have only S-wave collisions. So these are our simplifications we will follow during this lecture. Okay, so now let's start with our, what if you find the first formula in every theory paper. So after something like, we consider the system described by the Hamiltonian. Yeah? So we write the Hamiltonian. Of course, we have n atoms, as I said. So we have H. Let me write in traditional this form, sum of all particles. And then, of course, you have kinetic energy, I assume, n identical particles. Sorry, I forget. So here, identical. This is, of course, would be important for all the machinery. And then the Laplacian, in case you need, if you have a trap, you add here some trapping potential, here like harmonic confinement generated by optical means or magnetic field. So for ions, this very fastly rotate this electrical field. And then, of course, you have interaction, where you have sum over I less than j, some potential Ri minus Rj. And of course, we're looking for the wave function psi, which depends on all this nice set of coordinates, and which has to be properly symmetrized. And this is the way how the theory has been developed in the early days. People really write this wave function. So you can have a look in the textbook how nice they are looking. But of course, we will not go this way because we don't have much time and we don't have much space on the blackboard to write these wave functions. So what we will use, of course, a very convenient machinery, which is called second quantization. You already have elements of the second quantization for photons, so we can do exactly the same for atoms, for the many or for any many-body system. It doesn't matter, atoms, photons, electrons, ions, or whatever, molecules. It's a very generic scheme that allows you to very efficiently, in very intuitive pictures, if you wish, to present all the formulas and think about physics. Yeah? So we do this second quantization. So it is actually quantum mechanics. This allows to formulate the quantum mechanics not in terms of these wave function apparatus of that type, but in terms of occupation number of single particle states. Yeah, that is. Like in the previous lecture, it was occupation or number of photons in a given mode of electromagnetic field. So here, we don't have electromagnetic field. We have just atoms. So here, we need the number of particles in a given single particle state. So occupation numbers of single particle states. This will be Fock vector in a Fock space with n1, n2, etc. That tells you how many particles is in first, in a second, and third. And this is possible only because you have identical one. Yeah? Because they're all identical, the only things we need to know is how many sits in this particular state and that particular state, and so on. Yeah? So let me just, that we have all, so to say, common denominator, let me write some formulas here. Yeah? So generically, what you need here, you will need a complete basis. Let me write these formulas in a general case, but of course, for the box, we will choose a particular set, yeah, plane waves. So this is complete set. So I just write it in a more general form that you can also apply it for, let's say, trapped gases, not only for the box where we'll immediately use the plane wave. Complete set of single particle states. What does it mean? are complete, and of course convenient to say it orthonormal. So what does it mean? Orthonormal, of course, it's clear if I integrate. So here I just take the simplest case where I just have position. Yeah? Typically, you also have another quantum numbers. So that means there would be something here also. And maybe, well, then a nu would be extended. Nu is a set of quantum numbers that completely specify the single particle state. Yeah? If you have just free space, it's momentum. If you have a one-dimensional harmonic oscillator, it's quantum number n. Yeah, in a hydrogen atom is a main quantum number, angular momentum, a spin projection, so etc. Yeah. So here in this simple form, if I just integrate it like this, in a more general case, you need also summation over discrete indices. Yeah. And this is delta nu1, nu2. And another thing, now if I sum over nu, this is completeness. Phi nu R1, phi nu star R2 is just delta function. So that means any single particle state can be expanded in terms of this. Yeah? So here must be also some boundary conditions to really find these eigenstates. So this is more mathematics that was already mentioned by Jean-Michel in his lecture, that you need a boundary condition to completely mathematically set the problem. Yeah, but this is normal ordinary quantum mechanics. So now the question is, how can I description? So Fock space. So these are these. Yeah, with a vacuum state, etc., which has no n, 0, all n, 0. For this, to do this, you see already there is some ordering here. Yeah, and for bosons it doesn't really matter, but for fermions it will matter. So what we need here, let me write here ordering of single particle states. That would be important for fermions. For bosons, as I said, this is convenience. Yeah, if you write on a paper, you don't really need it. You need it, of course, if you program on computer, because computer has to know which state you consider. But on a paper, it's really not necessary. Yeah, we need ordering. For fermions, even on a paper, it is needed. So we need to know what is nu1 first, then comes nu2, etc. What are nus? Yeah? There is no general rule how to order them. Yeah, if you're on a lattice, especially on this one-dimensional lattice, it's clear. Here, 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 here. Yeah, how to order. Generically, it's very difficult. You can order them by the energy increase, for example. And if you have degenerate case, where some levels are degenerate, you also have introduced some rules how you order. But in principle, there is no general rules. It's a matter of convenience. Huh? So, for example, if you have two-dimensional lattice, that's already a problem. Right? You start either like this, then you go second line, or you go like this, or you go like this. You can have many options. Choose whatever you like. And then, now how to translate these things? This is just, I hope most of you know, but I want to have a collection of formulas that I will use. The link between apparatus in here and apparatus that acts on these vectors, yeah, set by this what is called field operator. It's actually psi on R in the simple case. For fermions, we will need an extra index, but for bosons, for our case, we don't need it. It is sum over all nu, phi nu of R, and then I introduce annihilation operator. This is my annihilation operator. I use a very strange convention. So here I put a hat for the operator in a second quantization, yeah, because this is just a complex numbers. Yeah, the difference of different positions, they're different. These are wave functions, yeah, just complex number. This is operator, annihilation operator that acts on this vector. So in general, this is operator, but it's position-dependent operator. Yeah? So I put here hat for the operator in this space, but here I don't put hat. Yeah, just because there would be so many a's that every time right hat it's a bit boring. And there is it's a with some index. We don't use these for any other things rather than annihilation operator. Yeah, so I hope there would be no confusion in these notations. Yeah? And of course, we have a conjugate field, which is the same sum with a complex conjugate wave of functions, and then a new dagger. And of course, I have to set up this commutational anti-commutation relation. Let me write it in a more general form. A nu 1, A nu 2 plus minus, or minus plus. Minus for bosons, it's commutator. It is this definition. A nu 1, A nu 2, let me put dagger here. Minus or plus A nu 2 dagger A nu 1. Yeah, that's the definition of this plus minus. So commutator for bosons, anti-commutator for fermions. And this is nu 1, nu 2, Kronecker delta. So it's only non-zero when nu 1 equals to nu 2. All the others are 0. A nu 1, A nu 2 equals 0. And A nu 1 dagger, A nu 2 dagger also equals 0. And here minus plus. For bosons, again, this is, you see that each mode means single particle state with a given set of quantum numbers, yeah, are independent because operators commute. Yeah, so therefore you can just to have a direct product, and therefore there was no problem. For fermions, it's a plus sign. Yeah, so even here, say 0, if you exchange, you get a minus. Yeah, so one has to be careful with this minus, and that's why we need the ordering to keep track of all these minuses. And this makes a difference for numerics fermions because you have to keep track of these minuses in this case. Okay, so this is the field apparatus. So now if you, using these conditions, you can, and actually the meaning of this field is this one annihilate particle at the position R, and this one create particle at the position R. Yeah? So you can immediately, using the relation between A, the algebra of A apparatus, and completeness of the set of the wave functions, single particle wave functions, so that you can see that psi apparatus satisfy this relation. And the others are 0. It just follows. You just use these definitions. Yeah, you commute or anti-commute, and then you use this. So clear psi with psi always commute because involve only A. We commute or anti-commute, the same for daggers. But psi with psi dagger, you will have A nu and A nu dagger commutator or anti-commutator gives you delta, and then you end up with a single sum like this, and then you get a delta function. Okay. So now these things, as I said, they are apparatus in the Fock space with position-dependent coefficients. Yeah. So how then we can translate apparatus? Just write down these formulas. I hope what I just said is in some form you are familiar with, in some form. If not, just come to me after the lecture for those who just see it for the first time or completely new. We can organize some crash course, a short one, pragmatical one, so that you can. But you will see the results actually very easy to identify and explain. Okay, how we can transform the operator translation. So how we can rewrite apparatus. So apparatus. In a single particle operator, let me call it H1, which has a form of sum over particles just a function f1 that acts on position of just a single particle. Yeah? And for example, for the Hamiltonian that we just have, this f1 of r is just always kinetic energy, right? But then you can have some external field if it's present in the system. Yeah? But it could be something different. So if I take f1, for example, in a delta function r minus ri, sorry, r0 minus r, or r minus r0, better, yeah, of r. What would it correspond to, the operator? Who can tell me? No, this single particle. So this would correspond to the following operator. It's n of r0, which is sum over all I, 1 to n, delta r0 minus ri. So just count the number of particles and a position 0. So it's a density operator. Yeah? And the total number operator, how can I write the total number operator? What should I put here? No, it's much simpler. Yes. So in this case, f1 of r is just 1. Yeah, because it's a strange form, represent the number n. Yeah. One of the way of represent the number. Yeah. So how can we now translate this operator, let me write it here, in a second quantization? So now I put a hat. So the rule is very simple. You just have to calculate this integral. That's it. If you have some additional indices here, which are responsible for the discrete variables, then you have to add a sum. This is very simple. No? So for example, if I look at these things, this is the simplest case to check, yeah, because then it's a delta function. Yeah, that gives me psi r0 dagger psi r0. Yeah. I put a delta function here, r0 minus r, then integral I can perform immediately, and it gives me this answer. For the total number of particles, it's just the integral psi dagger r psi r. Yeah, like the psi looks like a wave function in a standard quantum mechanics, but don't forget about the hat. So in the end, you will have, in here, if you just continue, so you put this decomposition for psi and psi dagger, then you use orthogonality condition. Yeah. So instead of 2 sums, you will get just 1. And then what is left is sum of a nu dagger, a nu. Yeah. You have already, this morning, this was exactly the number operator. Yeah. This a nu dagger, a nu, is just the number operator of particles in the state nu. Yeah. And here you just sum of all modes. It's very simple bookkeeping. Second quantization is actually very simple bookkeeping. You will see it. Yeah? So how can we write the let's say, Hamiltonian, which is probably most interesting part? Yeah? So for this, if we take the phi nu of r, eigenstate of h1 of these minus h bar squared over 2m Laplacian if there is an external field, then external field, yeah, with the eigenenergies epsilon nu, then the answer is very simple. H, let me call it 0, yeah, non-interacting single particle Hamiltonian, then you get a very simple answer. Sum of nu epsilon nu, A nu dagger, A nu. Yeah? I remind you from this morning, sum over n. Did you have polarization? Not yet, I guess. No? Okay. H bar omega n times A n dagger n. No. That's it. That's a very simple bookkeeping. This is counts you the number of particles in a mode nu, single particle. Then this number of particles you multiply by the energy of this mode and you sum over. It's very simple bookkeeping. So we are, so thin single particle we are finished. Let me look at the two particles, or the two body or two particles Hamiltonian. This is exactly this part. Yeah, let me call it H2 is sum over I less than J, or you can write it some F2 I J, or you can write it like this, sum over I not equal J, it's the same. Yeah, F2 I J. I took a very general case where this depends on, yeah, not especially homogeneous case, but you can write here minus simply, not a comma minus, because it's very typical for the interaction. It depends only on the distance between the interacting particles. So the answer is also looks very simple. The H2 now with a head is given by, okay, let's take this one, 1/2 integral dr1 dr2 psi dagger r1 psi dagger r2, and then you have this f r1 r2, or r1 minus r2 if you like. Yeah? Let me take the other color. And then you have psi r2 psi r1. The order here, just easy to remember. For bosons, again, it doesn't matter, because either these or this you can put whatever order you like, because they commute. For fermions, it does matter, because if you exchange, you get a minus. Yeah? And this is form easy to remember, because this is explicitly shows the Hermitian character of this operator, right? Because if you take Hermitian conjugation, remember, you have to make a conjugate of elements and reverse the order. Yeah? So this would be conjugated and be on the first. That's exactly where it stays. This conjugate after, etc. So you'll really get in this form, you really get this, that it is Hermitian operator explicitly, without any sort of small algebra you have to do. And that is the answer. So of course, if I now tell you how to write a three-body Hamiltonian, you will immediately tell me what should I do. Yeah, will the threefold integral with this combination of psi's, but we don't need to go that far. But in general, you can write whatever n-body Hamiltonian in this form. Yeah? And you see, so now they are really operators in a second quantization, so in the Fock space, which I erased. Yeah? In the Fock space on the vectors of the occupation numbers. Yeah? So they're redistributed of these particles among the single particle states. And of course, the most interesting case, let's just consider the interparticle interaction. Yeah? I just write down for you some intermediate formulas. Yeah. In a general case, probably this would, you can try to write it down. Yeah, dr1, dr2, psi r1 dagger psi r2. But in principle, this general formula you need only if you want really work in a harmonic oscillator or in a nuclear. But in a box, you will see that things would be much more simple. No? So this is a general form. You can plug in their compositions, but you cannot say anything. Well, if you have some selection rules, then you have an integral over four sort of products of single particle states. In general, you couldn't say anything except for some special cases where you have some extra selection rules, etc., etc. So now let me not bother myself with this general case. Let me just go to the case of the box, is what I said, because then things become particularly clear. So in a box, let me take phi nu of r in a form of phi p of r, yeah, because of particles with no internal indices, momenta completely set the single particle state, and I use it in this form. Plane wave, yeah. You may ask me what is the boundary condition you choose. So the answer, it will not matter, of course, in a thermodynamic limit. Yeah, so choose whatever you like. But I like this wave function. Yeah. You can take periodic boundary condition or zero boundary condition. In a sense, of course, this would be discrete if you have a box, but we will always take a limit v goes to infinity. So let me now take some table, yeah, because very often I will write sum over p, but of course I would never calculate sum over p. I will always translate it to the integral. So there are some rules for this. So if you have sum over p, yeah, when you want to calculate it, please go to the integral volume times integral dp, vector p means d3p, over 2 pi h bar cube. Then if I have delta p1, p2, yeah, in a box I have discrete. Yeah? So then it translates into 2 pi h bar cube delta function p1 minus p2. So I use slightly different convention for the Fourier, yeah, which is kind of more convenient for semi-classical physics. Yeah? You recognize here volume in a phase space, etc., divided by, yeah, okay. And then we also will need this integral over space, yeah, over all this volume. Let me write it like this, p1 minus p2 times r. We will also meet this integral. Yeah? So the answer is when p1 equals to p2, yeah, exponent is 1. I integrate over the entire space of my box, so I get v. But if p1 is not equal to p2, I have integral with the oscillating function, which to 0, yeah, integrates to 0. So these are the rules which will help you to do these calculations. Yeah, so now let me recover these things. So now let me continue with this interaction in this basis. Yeah? So of course what you will have is a big sum. Yeah, let me do it like this. So here I will use p1, here I will use p2, here I will use p4, yes, and here I will use p3. It's just easy to memorize with 1 odd, with 2 even, yeah, indices. No? So therefore, let me write the initial formula, and then I just make it 2 intermediate steps. And if you like, you can yourself, it's a good exercise to do the what is missing in between. Okay, I have 4 psi's, I will have 2 volume squared. Then I will have sum over p1 to p4. And then I will have AP4 dagger AP3 dagger AP4 dagger AP2 AP1. This is my apparatus that are hidden here. And then comes the integral dr1 dr2. And then let me write first volume interaction dr1 minus r2. Yeah, sorry for the using the same letter, but yeah, I hope you will not confused. I was once, but hopefully the last one. Yeah. And now comes the exponent. I over h bar. Now we have p1 minus p3 times r1. Yeah. This is r1 here and r1 here, and it's p1 and p3. And with r2 comes p2 minus p4 r2. Yeah, so this integral we have to calculate, and of course you see it's generically the case. Yeah, the interaction depends on the difference of r1 minus r2. So to make this to calculate to sort of continue, it is convenient to introduce the center of mass and the relative distance. Yeah. Such that inverse transformation is, of course, that you have r1 equals r plus small r over 2, and r2 equals big R minus r over 2. With this convention, Jacobian is 1. Yeah, but then you immediately see what happens. Yeah, you will not have here. There will be only dependence on r. Small r, sorry, small r. And all the big R dependence will be here in the exponent. Yeah? And and therefore integral over big R, yeah, because it's what I said is Jacobian dr1 dr2 would be just d big R, d small r. Yeah? This integral, because big R appears on the exponent, we can perform using this rule. And guess what it should give us? I just give you a hint. Translational invariance. Yes, momentum, exactly. This integral over big R, this gives us momentum conservation. That P1 plus P2 should be equal P3 plus P4. And the rest, you will have V of R here, and here would be some combination times R. And it gives us Fourier component of our potential. Yeah. So after this, and you see when you integrate over big R, you will have a volume. So you will have one volume less. So what you will get is the 1 over now 2 volume sum over P1 to P4 with the conservation law. Yeah, so it's only 3 independent. Then you will have AP4 P3 dagger, AP4 dagger, AP2, AP1. And then you will have V tilde, which is Fourier, of P3 minus P1. So this is one possibility. But then if I introduce this P3 minus P1 equals Q, the transferred momentum, you will see why I call it transferred momentum during the collision. That's my definition. Yeah? So from here, therefore, I immediately get that P3 equals P1 plus Q. And from here, then, yeah, I get P4 equals P2 minus Q. So I solve this constraint. So now what I get here, 1 over 2V, sum over P1, P2, and Q. Then comes AP1 plus Q dagger, AP2 minus Q dagger, AP2, AP1, V tilde on Q. Let me write somewhere this V tilde, how I defined it. So I put the 2 pi to the momentum integration, not to the positional integration. So it's a bit asymmetric. Mathematicians typically use very much like symmetric things, 2 pi 3/2 in both, but I prefer this. Yeah. So this is a very general form, and you can make a very nice picture of it. Yeah. So what it tells you, this was incoming particles with momentum p1 and p2. They collide, and they go to some new states, p1 plus q, p2 minus q. That's why q is transferred momentum. That it transferred from one particle, from p2 to p1. Yeah? But from point of view of second quantization, what happens? Initial particles in the initial states disappears because they collide and they go to some different states, and therefore here they appear. You annihilate the initial particles in the initial states and create them in the final states. That's, again, very simple, like a Lego. Yeah? Take from here, put it there, yeah? Or some whatever. Yeah? So the picture that you can write is like this. Sorry, somehow it traditionally goes from right to left. Yeah? So here you will have 2 particles, p1 and p2, that collide here and goes into p1 plus q and p2 minus q. And here is exactly the matrix element or amplitude of this process is exactly the Fourier component of the interparticle interaction. Yeah? That's a very simple diagram that describes this. And on a second quantization, it's simple. Yeah? You just annihilate these two because the initial state, they are not anymore there, and create them in these 2 states in the final states. Yeah, that's what they get after the collisions. Yeah? So it's a very simple things. And finally, final formula for the interaction. Oh, we are doing very well. Yeah. Now, of course, here stays some v tilde on q. This is a horrible thing. Yeah. So, but remember, we have a quantum gas, a low temperature, low energy collisions, only S waves. So therefore, we will use now contact interaction. When v of R1 minus R2, or R, let me put here R, we replace it with G delta of R, yeah, contact potential. Then, of course, V tilde of Q is just G. And remember, most of the time, you can safely write it like this, but not always. Yeah, we'll come back to this. Yeah, so therefore, in this case, things becomes extremely simple. Yeah, your now interaction Hamiltonian becomes simply G over 2V, sum over P1, P2, and Q. And now we have these particles after the collision, P1 plus Q dagger, A, P2 minus Q dagger. And here you annihilate particles in the initial states, and that's it. Now, this is our simplified form of the interaction part of our Hamiltonian. So now I can summarize things. And I write down the Hamiltonian of the gas we will work with for the rest of the lectures. Yeah? Of course, you know that's not convenient to work with a fixed quantum number, yeah? Like normally in statistical mechanics. What you do, you introduce the chemical potential, so you have the conservation of number on average. Yeah? You allow the particles go back and forth through the reservoir, so mathematics becomes simpler. For ideal gas, I guess you still can work with a fixed number of particles, but with interacting, I think it's a hopeless thing. So now finally the Hamiltonian, let me put here prime, that means minus mu n. Yeah? So this is actually H minus mu n. And write it in the following form. That is sum over P, yeah, box, epsilon P minus mu, AP dagger AP. This is our kinetic part minus mu. Remember what was the definition of the number operator, sum over PA dagger A. So that's exactly this part minus mu n. And AP is, of course, p squared over 2m. Yeah? Because our plane wave for the eigenfunctions of the Hamiltonian, of the single particle Hamiltonian, just Laplacian kinetic energy, with the eigenenergies p squared over 2m. Yeah, remember this sum over nu, epsilon nu, a nu dega a nu, with now nu replaced by p, and epsilon nu replaced by p squared over 2m. Okay? Plus g over 2v, sum over p1, p2, and q, and then the whole this structure there. A p3 plus q, dega a p2 minus q, dega a p2, a p1. Okay. Yes, thank you. Yeah. So this is our Hamiltonian for both bosons and fermions. The difference is that the algebra, yeah, commutators for bosons and anti-commutators for fermions. But for fermions, of course, we will need more because we're S wave, so we have to add here some extra index. But it would be very, very much similar. At the right moment, I will tell you how to make this difference. So it's really trivial things. Yeah? Okay. So this is our many particles Hamiltonian. So let's start with the simplest case. Let's start with bosons. And moreover, we start with the ideal bosons. Ideal boson gas, BC. I just remind you some facts, known facts, hopefully for you, about the BEC, and tell you some things which not necessarily you find in the textbooks about the BEC. So let's now start with this H0 prime, which is sum over p, epsilon p minus mu, AP dega AP. Yeah? And of course, what we also want, so we want to find what's the ground state or what is the equilibrium state, let's say at some temperature. This is a temperature we specify. Let's start with the higher temperature before BEC, where it was, okay, temperature. So at least larger than this T star that we described. Yeah? And then what we want also, as I said, we can have this, the basic equation here is, of course, the number. Yeah, we have to have a fixed number. Well, not a fixed, but on average. We have that the average of these things, sum over p, AP dega AP, over our equilibrium state, which is the same as sum over p and p, yeah, over our equilibrium state at temperature T, is fixed. Yeah? Yeah? So we want to find what is the low state, typically what is the low energy state, etc., etc. Yeah. So how we proceed? We just, let me clean here the blackboard. So we know that this average at temperature of NP is given by Bose-Einstein distribution. Yeah. So I just plug it in, and I have, let's say, let me put n. This is just this is this n average, yeah, which I fixed is sum over all p. Let me do here a bit more details. Yeah, sum over all p of these Bose-Einstein occupation numbers, and now, of course, I use my table and translate this sum over p into the integral. So it is volume integral dp, and then I have 1 over e to the, let me write here, p squared over 2m minus mu minus 1. Yeah? This integral I have to calculate. First of all, of course, let me go a little step back. If I look at this expression, yeah, clear that here, from a purely mathematical reason, of course, there is a physical reason behind. Mu has to be negative. Only because positive mu formally will create singularity here. Yeah? Because if mu is positive, at some p, epsilon p will be equal to mu. So you have 1 minus 1, you have 0, you have infinity. And moreover, you have on one side of this infinity positive n, on the other side of this infinity negative n, which is, of course, nonsense. Yeah? Physically, what it means, there is a physics behind, of course. What is chemical potential? The energy that so to say, that you put, so minus mu is this, you have a bath, let's say, with a zero energy, and minus mu is the offset of your system, low energy, which you put up or down. You have to balance the particles coming in and out. If mu is positive, you put it down. Because particles are non-interacting, in this case, where you have a water reservoir with a level here, and your system is there, you have infinite number of water, or let's say particles that come in your system. Yeah? So you have to put it up to have the number of particles fixed in your system. You have to go up the lowest level in the reservoir to have a fixed number of particles. For the interacting case, this is not necessary, because if you are in the interacting case, mu is positive, you go up, you put particles there, but then interparticles repulsion will keep the density fixed. Yeah? But for ideal, it must be strictly negative, or in a more general case, if you have a trap or things like this, discrete spectrum, or for some reason, mu has to be below than the lowest energy state of single particle lowest energy state. With momentum p, it is, well, almost zero in the box, depending on the boundary conditions. But yeah. So now, of course, sorry, I forgot divide by t. Yeah, I don't have space for p squared over 2m minus mu divided by t. Yeah. So then, of course, the story can be told in two different ways. Standard in the textbooks, what you do, you say, well, okay, let me decrease the temperature, cool my system, and see what happens with this equation. Yeah? At some point, you see that something goes wrong. But originally, in the Einstein paper, it was done in a different way, and was done, okay, I have my box at some temperature, and I just want to add particles with the same temperature. You will see it's exactly the same. So let me just see what happens if I start put more and more and more particles in my box. Yeah? So we have to balance this. If I increase the left-hand side of my equality, I have to increase the right-hand side as well. This is fixed. This I integrate. So the only option that I have, let me write it like this, is to decrease more n. I need less or smaller modulus mu. Yeah, because then this becomes smaller, the fraction becomes bigger, so integral becomes bigger, so that makes me happy. Yeah, so I can balance, but then I put more and more and more, and at some point I come to the point where mu is 0. Yeah? This is the lowest value for the modulus mu. And now, of course, the question is what happens with the integral. As you will see in low dimensions, the integral will diverge. In 3 dimensions, it doesn't. Yeah? Because in 3 dimensions, at finite t, what you will have this 1 over. So the difficulty is, of course, 0 momenta. At high momentum, this is exponentially suppressed, so fine. At low momentum, p goes to 0, you will have these things. This is 0. No? This goes to 0. T is finite. So it goes into 2mt divided by p squared. Yes?
I didn't catch that. Why does mu get smaller with more n?
look at the integral. That's the only way how you can make the integral larger. When you fix t and over p you integrate.
And why do I want to make it larger?
Because I want to make n larger. I want to put more particles in there.
Yeah.
Yeah? And then, of course, you have from the integral measure, you have p squared dp. Yeah? So you see you have a linearly divergent integral. Yeah? Oh, sorry, convergent integral converges at small, at p goes to 0. P large, of course, diverges. So it's convergent. Yeah? So therefore, you will have some critical number of particles which corresponds to dp 2 pi h bar cube 1 over p squared over 2mt minus 1. But the question is, if I want to put more, yeah, and there was a question asked, I guess, by Einstein, and he said, who is the master, I or this reservoir? Yeah? I put it there. But how can I satisfy them this condition? And of course, the gas, and you know the answer, they should go to the state with momentum 0. Extra particles this is a BC. So this gives you at a given temperature, yeah, whatever temperature you give me. And I think it's a paper has some title, in a title states limited capacity of the Bose reservoir at a finite temperature. Yeah. Up to here, you are in a Bose-Einstein distribution. Above, the difference should go to the p equals 0 state. Yeah. So of course, we used to slightly different setup. So we fix n, which is n over volume is fixed. So we want to know, so the canonical way nowadays from the textbooks, I fix n and I decrease the temperature. It's exactly the same story. Yeah. So at some point you will see that you rise to the point below the temperature below which you cannot, because mu is actually temperature dependent. Yeah, so here we have mu on T. We have to balance both. So if you decrease T, you have to adjust mu. So then you will end up with the following relation for the critical temperature. So this is the lowest temperature where you can still put all particles in a Bose-Einstein distribution without particular macroscopic occupation of a single state. And of course, the integral you can relatively easy to calculate. First of all, you write 4 pi as an angular integral, 2 pi h bar cube here. And then you have integral p squared dp with this fraction. And of course, you do it dimensionless. Yeah, so you absorb these 2mtc into p. Yeah, so what you get is like this. Let me write, okay, let me write all the coefficients that is clear their origin. And then you will have 2mtc to the power 3/2, yeah, because I have to rescale p with square root of 2mtcx, yeah, where x is now dimensionless. It's always useful to go to dimensionless integrals. And then you have an integral to infinity dx, x squared over e to the x squared minus 1. Yeah. In this integral, I give you hints, and then who are interested, just try. Zeta, so it comes the sum. Integral you can reduce to the sum in this integral. So this is zeta function with the argument 3. And this is square root of pi over 4, this integral. Yeah. So finally, you have some expression which relates you Tc with n, with your concentration. From here, of course, you get the famous formula. Let me write down the 331 I remember, but I don't remember this nice coefficient, which is actually quite simple. Yeah? 2 pi over zeta, and zeta over 3, I think, is something like 1.772. And then to the power 2 or 3. And then comes this h bar over m, n to the power 2/3. Yeah, remember, this is our T star. Yeah? That was our T star estimate. Yeah? So indeed, this is 331 h bar squared over m, n to the power 2/3. That's exactly where we expect that quantum effects enters into the game. And physically, that means in the ideal Bose gas that now macroscopic number of particles starts sitting on a state with p equals 0. Yeah? So what now we have for this temperature below Tc, remember, this was determined by the fact that mu is 0. Yeah? So now below Tc, we don't have mu anymore. Yeah? But now balance should be included this n0, where n0 is, of course, n0 divided by volume. No? So this particle sitting with p equals 0, no? Which you add. Integral does not fill the occupation, the value. Remember this mathematical analysis. Integral is insensitive to the value of the function at some set of points, which even has a measure 0. So just here is a single point. Yeah. So plus integral dp over 2 pi h bar cube, and then 1 over e to the p squared over 2mt minus 1. Yeah, and now you can very easily evaluate this integral, and you get a famous result. So what you do here, simplest way is just scale p to p times square root of t over tc. Why it helps? So here dp3, right? So you get t over tc to the power 3/2. And the rest times the integral dp 2 pi h bar cube 1 over e to the p squared over 2mtc minus 1. Yeah, but now if you remember the way we define tc, so you know the answer for this integral. Yeah? With tc, you know the answer. It's exactly the density n. So all this integral is n. So now you have a very simple equation. N equals n0 plus t over tc to the power 3/2 times n. Yeah? And now easy to solve. You get n0, this very famous formula, n1 minus t over tc to the power 3/2. So in this macroscopic fraction, when t below tc, it is non-zero, and it sits in a state with p equals 0. Yes?
This was all a bit fast for me. So could you kind of explain more in the beginning, where we kind of start with changing the chemical potential, and then we move to changing the temperature?
No. Here, yes, there are two ways. There are two ways of getting to BEC. Initially, historically, the temperature was fixed, yeah, but number of particles was increased. Yeah? So therefore, to balance this equation, we have this we increase, and here the only thing they can adjust is the chemical potential.
Okay,
yeah?
so that's not a very physical system. That's a very hard to engineer system.
Why? Well, I think why not? You have a box, you put more and more particles, inject more and more particles.
Yeah, but keeping the temperature.
Yes, but you have a big reservoir. We always, this is quite natural, yeah? Just attach yourself to the radiator and then you're fine. Yeah? Yes, that was kind of, initially it was discovered that this system, if you rely upon only this distribution, had a finite capacity. With this distribution, you cannot put more than some critical number, depending on the volume, of course. The concentration of bosons inside, if you rely upon this distribution, cannot be larger than some critical value. This critical value depends on the temperature. Yeah? For a given temperature, given critical value. You can reverse this, and it's there.
So the critical value is the kind of amount of atoms I have to put in until it DC forms?
Yes.
Okay,
Yes,
so
yes.
I just
You
shove
can,
more atoms in
and they put on P equals 0, okay?
that's still one.
But you can reverse the system, reverse the things. Yeah? If you have critical concentration that corresponds to a given temperature, if I now fix the concentration, you will get a critical temperature, above which it's all fine, below which you have a problem, the same problem. You can go and actually analyze the same equation, the same formula here, yeah, using fixing n, and now starting to decrease the temperature. You will come to the same conclusion, but for this you have to decrease the modulus mu, but it has its end, yeah, this process, when modulus mu is 0, and that's what corresponds to some critical temperature. You see mu is 0 here, for a given concentration, so it's reverse. Yeah? But you see the formula is exactly the same.
Yeah.
So here I call NC, yeah, and here NT, yeah? But here I have N, but TC. So it's the same.
So does that actually mean that if I had ideal bosons, I could always get a DC by just shoving enough of them in the box?
Oh, cool.
No matter the temperature?
Oh, cool, yes.
Yeah.
Oh, cool.
Okay, and that's only then ruined because I don't have ideal bosons, I guess. So
in ideal gas, in a weakly interacting gas, there wouldn't much change. You will have exactly the same story.
Okay, so
in the weakly interacting. Yes, you have to put.
Generate hot DCs.
Yes, but that was if you know the history. When next week ask Jokvalraven, yeah, when they first tried to boson condense the hydrogen, yeah, because their TC is the largest one, yeah, and the problem was to get a large phase space density. Yes, right, phase space density. Yeah, and there you can reach a two-way. So you have to either cool, then you contract the momentum distribution, or you put more particles. But unfortunately, cooling is always limited, yeah, because at low temperature you have all these collisions and the thermalization, etc., etc. But number of particles was limited by some inelastic things on the walls, etc., etc. So there was a big science behind. There was a difficulty in that. Yeah, yeah. So there are two ways to reach. Yeah, either more particles or low temperature. Yeah.
When you say boson into P equals to 0 state, then does it mean like the essential momentum of them are quite 0, so they're
Momentum is 0. Yeah, but they go to the lowest state in your system. Yeah.
okay.
In a trap, they will go to the lowest state of the harmonic oscillator. Yeah. So here it depends which boundary condition you choose. Yeah. So you can choose a periodic boundary condition, and the lowest momentum is 0. But now I think I will have time to explain you something. If I took the 0 boundary conditions, yeah, then of course the lowest energy state would be non-zero, but something like 1 over L squared behaves. Yeah. They all go to the lowest energy state, and this always happens. Yeah. And it's for a three-dimensional case, these things happens in a finite TC. Yeah? And tomorrow I will discuss a bit Bose-Einstein condensation in different spatial dimensions and in different traps. When you always have BEC in the ideal gas, is that T equals 0, always. In whatever dimensions, ideal gas, stress especially, ideal gas, T equals 0, all particles sits in the lowest state. Lowest energy state, by definition. Yeah? They are all, the ground state is all particles sit in the lowest energy state. This is BEC. The question is not to have BEC at t equals 0, which is unreachable. At some finite TC. In a discrete system, when you have trap, for example, the question is, of course, you don't have in a finite system phase transition like what we have here. You have a kind of crossover. Of course, you are interested when this TC is much larger than the level spacing. Okay, so good. So now we know that the t below TC, we have mu equals 0, but we have n0 as a kind of new variable. And now above TC, we don't have n0, but we have mu. Yeah? So that's how you balance the equation for the average particles number. That's the solution of these things. Yeah? Below TC, we have a condensate. So now I want to discuss with you one subtle thing, yeah? Which is actually how zero is this zero. Yeah? What kind of zero you have here? Yeah, what I said, this one. It's a mathematical zero or microscopic zero or what do you think? Is it strictly mathematical zero? Who vote for that? Oh, clever people. So let me, for this, and also to see how a bit of a more structure about this state at the finite temperature. At 0 temperature, it's all clear. Ideal gas all sit with P equals 0, so nothing to discuss. No? Let's look at the finite temperature. T some below TC. Let's have a closer look how these distribution look like in this, and then we find also the chemical potential, how it approaches, okay, 0. So let's consider now box, and I put a 0 boundary condition, L, 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 and just to be specific, I put 0 boundary condition. It doesn't matter. You can repeat yourself just to check whether you understand or not for periodic boundary condition. Yeah? It actually won't change much the consideration. Yeah? In the box, we know that the energies in the box, I have 0 boundary conditions. So then we have the energies in the box, E and X and Y and Z are pi squared h bar squared over 2m, and then we have nx squared plus ny squared plus nz squared. And of course, these things has to be positive, because if it's negative, the wave function is 0. Yeah, the wave function, remember this sinus in this case. Sinus pi h bar nx over L no. Sinus pi ny over L y times the sinus pi nz over L times z. These are the wave functions. Yeah, so n has to be strictly positive, because otherwise the wave function is 0. For periodic boundary conditions, that's not the case, so you can use a plane waves, then you're allowed to have a 0 moment. But just let's take this one, and you check the simplest case periodic boundary condition, if you like. Yeah? So therefore, the lowest energy state that corresponds to all of them are 1, yeah, the lowest possible value. You have pi squared h bar squared over 2m times 3. The first excited state is 3 times degenerate. Yeah, when one of them is 2 and the others are 1. So then you get E1. Okay, E1. Okay, let me write epsilon. Yeah, just single particle energies, we use epsilon. Epsilon 1 is pi squared h bar squared over 2m times 1 plus 1 plus 4 is 6. Yeah? So let me just, and sorry, I forgot L squared and L squared, these ones. So let me just, to make clear the conditions that I will consider, let me take the difference, epsilon 1 minus epsilon 0. What's the level spacing? Yeah? And clear, forget about 6 minus 3. So it's of the order of h bar squared over m L squared. This is typically what you have a level spacing in a box for the low energies, when this n squared will not start dominating. So let me now do the following. Let me divide by n to third and multiply it by n to third. And I did it because then these things, as you can see, it is actually in this box, it is actually n divided by volume to the power 2/3. Yeah? Because volume, V is L cubed. If I take L cubed to power 2/3, I get L squared. And here n squared. Yeah? So this is actually concentration to the power 2/3. And then you see that these things is 1 over n 2/3 times of the order, okay, this time times h bar squared over m n 2/3. But we know already this combination, yeah, what it is. So we know that, let me write it here, that epsilon 1 minus epsilon 0 is of the order of Tc divided by n to the power 2/3. Forget about 331. Yeah? So now let me consider now my temperature. T is much larger than epsilon 1 minus epsilon 0, but smaller than Tc. I don't want to go to these microscopically smaller temperatures. Yeah? So it's real one. No? So this is my temperature. I'm a condensate regime. Yeah, but my temperature greatly exceeds the level spacing. Yeah? So now let me have a look what happens in this. So now let me start with my n. Let me write the same equation for my distribution functions. So it is, let me specify lowest energy state. Yeah? So we'll have 1 over e to the, so now I don't have integral, I have a sum, so I have to be careful with each term. Yeah, it's only under the integral I don't feel a particular point. So here I will have epsilon 0 minus mu over t minus 1, yeah, plus 1 over epsilon 1 minus mu over t minus 1, and here I have to add 3, yeah, because this is a degeneracy, yeah, etc. This is degeneracy of my level. Yeah. So now I make an ansatz that you will see works. Yeah. So that epsilon 0 minus mu is much smaller, then you will see that it works. Otherwise, I cannot solve. Yeah? But now I will be able to solve. Why is this? Because now if I consider epsilon 1 minus epsilon and epsilon mu, or all the other, yeah, then you can write it epsilon 0 minus epsilon 1 minus epsilon 0 plus epsilon 0 minus mu. Yeah? And the second is much larger than this one, and for sure much smaller than t, etc. So this, for all the other levels except for 0, that means I can throw away my mu. So therefore, I continue here. What I write is 1 over e to the epsilon 0 minus mu. So now I want to find the equation for these things. Plus, and now here, these are degeneracies, and this one is simply epsilon n minus epsilon 0 over t minus 1. And this is what you would call n prime. This is a particle that I sit. Yeah, you see, in the microscopic limit, they don't have mu anymore. So now if I go to the big box, that's exactly what I would have. And this is my lowest energy level. Yeah? That should be my condensate. All the rest is n prime. And let me write for this what I know, assuming the big box, v goes to infinity, n goes to infinity, n over v fixed. I can write this n, what I have it there, right? I have it n times t over tc to the power 3/2. Yeah? And this one, so this I know. And the first term, you see, I have two conditions. First one, this one, and the second, this one. So that means that here I have that my epsilon 0 minus mu is much, much smaller than t. So I can expand. So therefore, this I can expand. This is a small number, therefore. I can expand my exponent in the Taylor. Unit cancels. So what I have here, I will get t divided by epsilon 0 minus mu plus n prime. And if I look carefully, what you see here, that you get this t divided by epsilon naught minus mu. If you combine both sides, you will see that it is actually the condensate fraction. Yeah? n 1 minus t over tc to the power 3/2. This is, remind you, this was n0, yeah? In our case. So now we can solve it. We can solve it and see that it actually mu from here, what do we have? We have convert this. Okay, we have mu now becomes epsilon 0 minus t over n, and then we have also these things, 1 minus t over tc to the power 3/2. Important point here is this one. So you see, at t equals 0, mu goes into epsilon 0, that it should be, that all particles sit in the lowest energy state with epsilon 0. Otherwise, below Tc, it is non-zero, but it's macroscopically 0. So you see, this difference is 1 over n. So it's macroscopically 0, as long as the number of particles is very large. It is 0. So this actually answers the question that it's not exactly 0. It's 0 only in the thermodynamic limit, right? If I set n to infinity, this goes to 0. This actually, if you use a periodic boundary condition, would be 0. In my case, it is not, but if you use periodic boundary condition, this would be 0, and this would be exactly the chemical potential we discuss. Yeah? Okay, so the last things that I want in the last 2 minutes to discuss. So this we know that n0, let me write it here so it's the same formula. n0 is n times, so it's of the order n. Yeah, it can be 2/3, 1/3, depending on the temperature. Yeah, but of the order n. Let me now calculate the number of particles in the first excited states. Not in n0, but the next one. Yeah? So for this, remember, we can forget chemical potential here. Yeah? You will very easily, yeah, okay. So then it gives me 1 over e to the epsilon 1 minus epsilon 0 over t minus 1. Yeah? And epsilon 1 minus epsilon 0 is this quantity. You see, it is very, very small. Yeah? So if t is not extremely small, Then you can also expand this. This is a small number, yeah, because we don't go to the temperatures which are comparable to the level spacing. So it is T divided by epsilon 1 minus epsilon 0. And if I put now this estimate for the level spacing, so I will get T over Tc times n to the power 2/3. What we see here, when t goes to 0, indeed n1 goes to 0, all sit in a state 0, yeah, the lowest energy state. But if t is non-zero and not macroscopically small, yeah, that this fraction, let's say 1/10, yeah, we have n to the power 2/3. Large number, very large number. But if I made a ratio, but still it's 2/3, it's less than 1. If I made a ratio of this number to this number, I get it is 1 over n 1/3, much smaller than 1. So what it tells you that if you have BC, it's indeed one level is macroscopically means of the order of total number of particles. Macroscopically occupied. It's the lowest energy state. But all the other state, at least low energy state, occupation numbers are large. Yeah? They are macroscopically smaller than in the ground state, but they are still much larger than 1. And this is actually the reason for this Gross-Pitaevsky description of the Bose gas. Because you will heard, I guess, when you look about the laser, it's a practically classical field. And a classical field, when it has a large occupation number, yeah, then you can forget about this 1 in the commutator of the bosonic apparatus. We will come to this point, I guess, next lecture when we start interacting Bose gas. So low energy state behaves like a classical field because they have a very large occupation number. It's not comparable to the total number of particles, but it's still much larger than 1. So therefore, a mean field description for the Bose system, the same true would be for the interacting case. So therefore, the mean field description of the bosonic system is so successful. Yeah? Because of the large occupation number of a low energy state, but low energy state it is smooth in space and time. It's exactly where you have Gross-Pitaevsky description. I finish for today. Questions? No questions? Good. Everybody hungry. Okay. Then.